All right, everybody, welcome back to chapter 4. So we're moving on to dilutions, and those are pretty much exactly what they sound like. You have a compound in solution, and you're changing the molarity, the concentration of the compound by adding water. So the real key to this, as you see, is that the moles of your solute after your dilution equals the moles of your solute before your dilution. So that's going to be how you really work with problems. So it's like if we dilute 500 milliliters of 18 molar sulfuric acid to 6 molar sulfuric acid, well, the moles of sulfuric acid are not going to change. So we could probably figure out what those are. We could say, well, let's see. I'm just going to work in liters because I have molarities and that's moles per liter. So if I have 0.5 liters of my sulfuric acid, and my original sulfuric acid is 18 moles, and I calculate this out, this is going to give me 9 moles of sulfuric acid, and that's what's going to be in both solutions. And then I say, well, I want to get my new volume. But I know this time I want it to be 6 molar. And so again, moles per volume. This time I'm going to divide by the molarity, 6.0 moles per liter. And of course, you see liters cancel, it divides out, moles divides out. This will give me 1.5 liters or 1,500 milliliters of solution. So that's what I'm going to be doing. I'm going to be, I say adding water until I increase my volume to the point where the concentration has changed. But you'll find out your 18 molar sulfuric acid is what we know is concentrated, and you don't add water to the acid. You want to add the acid to the water, or else you can get a very violent explosive reaction. But still, the overall calculation works. Now, what we can do is we can use this calculation to find a very important mathematical relationship that we're going to use. So if we label these, this is calculation one, this is calculation two, you notice that calculation one is going to be, hang on, that's not volt. This is going to be volume one times molarity one, and then we're going to take again M1V1, and then we're going to divide that by molarity 2. And so this will be M1V1 divided by M2. And what we notice is what we get out of that is our second volume. So we can start there saying, well, if M1V1 over M2 is going to equal my second volume, that means I have a relationship of M1V1 equals M2V2. And so you see that right here. This is something you'll use a lot in dilution. So the M's are your molarities. And so M1V1, that's your first concentration and its volume equals the second concentration and its volume. So you're just going to move this equation around to really figure out what your dilution should be. So let's see. how would we prepare 1 liter of 0.5 molar solution of nickel 2 chloride? Make sure you can still name these, because remember, each chloride is a -1. If I have two of them, that means that nickel must be a 2 plus or nickel 2. Let's see, from the salt hydrate, nickel 2 chloride hexahydrate. All right, so remember, we want to state what we're being asked. And then let's see some things that we know. The volume we're after, 1 liter. Nickel is going to be, look at the periodic table, 58.69 grams per mole. Chlorine, 35.45 grams per mole. Hydrogen, 1.01. And oxygen is 16 grams per mole. Okay. So we want the molar mass of this entire hydrate, because if we just did a straight calculation using only nickel chloride, we're not going to get enough nickel chloride. We want to make sure we incorporate all the mass of the entire hydrate. That way we know when we get our specific amount of nickel chloride, it has the proper number of moles in it. So it's going to be nickel plus 2 chlorines plus 6 H2O, so it's 2 H's plus an O. It's going to be nickel plus 2 chlorines plus 12 hydrogens plus 6 oxygens. Plug our numbers in. Okay, so this is going to give me 237.71 grams per mole. And so we know in 0.5 molar nickel 2 chloride, we have to have 0.5 moles. And you, again, using this entire molar mass will ensure that we get the proper number of moles. Because again, if you look for, all we need is 0.5 moles of the hydrate, because you see for every mole of this hydrate, we get 1 mole of the nickel chloride and 6 moles of water. So again, if we just incorporate the entire hydrate, we'll get enough of the nickel chloride. Okay. How much do we need? So pretty easy calculation. So it has to be 0.5 molar, 0.5 moles per liter, multiplied by 1 liter. So we're going to need 0.5 moles of nickel chloride, nickel 2 chloride in the solution. So then that makes us say, well, What mass of the hydrate are we going to need to accomplish this? Okay, so I know I need 0.5 moles of the entire thing. And I know that the hydrate is 237.71 grams per mole. This is going to give me 119 grams. Okay, now that you know you need about 119 grams of the hydrate to to get the proper moles of nickel 2 chloride, the way you prepare it is you're going to say, so again, you start by dissolving your solid hydrate in enough water to completely dissolve the whole thing. Then if it's already in the flask, that's fine. If it's in a beaker, you need to transfer it to a flask. And then you're going to dilute this solution. And so that's how you prepare it. So again, you want to figure out how much you need. Then you're going to put it in enough water to dissolve it. Make sure it's then either in a flask or transferred to a flask, and then finish the dilution with water up to 1 liter. Okay, so here, how would you prepare 1 liter of 0.5 molar solution of sulfuric acid from concentrated or 18 molar sulfuric acid? Remember, that 18 molar is your concentrated acid. Okay, so if this is the solution we're preparing, that's going to be our second volume and second molarity. So our M1 is going to be that one. So what we're being asked for is what is the original volume that you need? Oh, let's see. So we know V2 is 1 liter, 1,000 milliliters. M2 is 0.50 molar, and M1 is 18 molar. There's the things that we know that'll help us solve the problem. This time, our theorem, M1 V1 equals M2 V2. V1 is going to be M2 V2 divided by M1. And now we can plug in numbers since we've done our little bit of algebra. Plug in M2, plug in V2. You could have left it in meters. I would accept that on homeworks. It makes more sense in milliliters because most of your measuring equipment in labs is in milliliters. And when you calculate this, your V1 is going to be 27.8 milliliters. Okay, now the way you're going to prepare this, because again, you always want to make sure that when you're preparing something, like your entire solution can't be more than 1 liter. So you have to figure out how to get there. And again, this is a strong acid, so you want to add it to water so you don't get an explosive until it's more dilute. Once it's more dilute, it won't matter. But when it's concentrated, you want to make sure you're adding the acid to water. So a good way to do this, you're going to measure out about 800 milliliters of water. Okay, then you're going to slowly add the acid to that amount of water. Then you're going to have a little bit of room left before you're up to 1 liter. So see, now that you've added the acid to the water, the concentration's much lower. So the explosive effect is going to become minimal or disappear. So now that you have this non-explosive solution, you'll finish diluting to your 1,000 milliliters or 1 liter. Again, you want to, and when I say explosive, I'm not talking like, I don't know, like a firework. But what I'm saying is, if you put the water on the acid, it's going to start to fizz and bubble and pop, and it will pop out on your skin, and you really don't want that to happen. Okay, precipitation reactions. So we've been talking about this a little bit. Sometimes when you mix solutions, not every you have a bunch of ions in solution. Not every pairing of ions is going to be soluble. We talked about the solubility rules. If you mix solutions together that have ions that can form um, an insoluble salt, those ions are going to combine to form a solid. That solid is known as your precipitate, and that's a precipitation reaction. Here, you see we have our copper 2 sulfite mixing with sodium hydroxide. You're going to get your sodium sulfate, which is still soluble, but your copper 2 hydroxide is not soluble. So when those mix, that copper 2 hydroxide will fall out of solution as a solid. Now, I went ahead and put this little arrow on here. I'm not always going to use that, but you will see that in textbooks or in different places. And that little arrow means falls out of solution. You'll see another one that's an upward arrow, and that's usually for a gas. It means the gas comes out of solution, just as long as you're getting used to the terminology. So then the question is, can we predict the products of a reaction? So what if we mix sodium hydroxide with magnesium chloride? Now, you see how I asked this question here? You're going to want to make sure you're still working on your naming and writing formulas from names, because I will ask questions in this way. Okay, so for mixing sodium hydroxide, let's see, with magnesium chloride. Okay, so that means, oh, what is sodium hydroxide? Magnesium chloride. Okay, so each chloride is a -1. Magnesium has to be a +2. It's in the second column. Sodium is a +1. It's in the first column of the periodic table. And then our hydroxide is a polyatomic at a -1. So that means we're going to be mixing magnesium chloride plus sodium hydroxide. And actually, I want to back up a little bit. Remember, we have our solubility rules, so you want to go check those. And you'll find that your magnesium chloride is aqueous. Your sodium hydroxide is aqueous. For example, this sodium hydroxide is soluble by rule number 1. So again, you're going to want to go back and check that. So then the question is, What are the products of this reaction going to be? Now, let's go ahead and write these. What are all the ions that we have present? Okay, well, we have magnesium. This is where you're going to want to start watching. Ions will only exist in the aqueous phase. So if you have any other phase, you're going to start to get things marked wrong. Let's see. We have our chloride ions. We're going to have our sodium ions, because again, if these are aqueous, they dissociate in solution. They dissociate in water, which means they're going to be existing as basically a solution of ions. And we're going to have hydroxides. Now, we know that cations have to pair with anions. We have to pair a positive with a negative. And for these to repair with their original if your anions pairing with their original cations doesn't make a lot of sense, because that would just put back together a molecule that's soluble. It would just immediately dissolve again. It doesn't make sense. So what's going to happen is your cations and anions are going to swap. So what you're going to get then is your magnesium is going to take the hydroxide and your sodium is going to take the chloride. Okay. Now, why did I do that? I didn't need parentheses. Use parentheses on polyatomic. Oh, yeah. Your magnesium is going to take the hydroxide. That's why I did it. Okay. So now we're almost there. So we say, what are the phases on these products going to be? Sodium chloride is soluble by rule 1. Magnesium hydroxide is insoluble by rule 7. So that means one of them's aqueous, one of them's going to be solid. And then if you notice, you have to balance this. I have one hydroxide, two hydroxides. That's not going to work. I have two chlorides and one chloride. That's not going to work. So what I'm going to have to do is say, well, there's my magnesium chloride. And then I'm going to need two of my sodium hydroxides. Okay, I'm going to need two of my sodium chlorides. And rule 1 says this is soluble, so this is an aqueous compound. Rule 7 says magnesium hydroxide is not soluble. So we get a solid. We have a precipitation reaction. Also notice that this is a double replacement reaction. So again, your precipitation reaction is a type of double replacement because again, your sodium and chloride went to your sodium, and your hydroxide went to your magnesium. So double replacement. All right, let's work on a few of these. When the following solutions are mixed together, what precipitate, if any, will form? Okay, well, can you name this one? So you see we have sodium. We know that each sodium is a 1 plus. There's two of them. So whatever this is has to be a -2. and that is your chromate ion. So you have sodium chromate. Uh, you could figure out aluminum. You remember aluminum is a common charge at a +3. Each bromine is a -1. If you didn't remember aluminum, you'd say, well, if I have three bromides, that's going to be a total of -3. What does aluminum have to be to neutralize that? Well, it has to be a +3. Okay, so what are we going to get? Let's break these down into their ions. You see, you get your sodiums, get your chromate, get your aluminum ions, your three bromide ions, and let's see. So again, original cation anion pairs are not going to come back together because again, that would just recreate a soluble compound and it would immediately redissolve. So the ions are going to switch places. We're going to get another double replacement. And so what we're going to get is sodium bromide, which of course each sodium is a +1, each bromide is a -1. And we're going to get, okay, so aluminum is a +3, chromate is a -2. So those can only come together at a charge of +6, -6. So if aluminum is a +3, I have to have two of those to get a +6. Chromate's a -2. I have to have three of those to get a -6. So there's your aluminum chromate. Okay, now sodium bromide is soluble by solubility rule number 1. Aluminum chromate is insoluble by solubility rule number 10. So we're going to get a precipitation reaction. All right. Okay, so sodium chromate plus aluminum bromide. That is going to give us sodium bromide, which is aqueous, and aluminum chromate, which is solid. And then, of course, we want to make sure we balance it. And so we go through our process for balancing, and you'll find that we're going to get 3 sodium chromates plus 2 aluminum bromides. And then we're going to get 6 of our sodium bromides. And then we just have the 1 aluminum chromate. And there's our precipitation reaction. Okay, so can we do it again? Up here we have, oh, so you can't call this nickel nitrate because remember nickel is one of our it's one of our transition metals. It's going to be and it's not one of the exceptions. So it's going to be a variable charge ion. So this, okay, so if each nitrate is a -1, we know that because we should know what nitrate is. I have 2 of them. That means 1 nickel has to have a charge that cancels out 2 -1s. So nickel has to be a +2, so it's nickel 2 nitrate. Then you see we have calcium chloride. So again, chloride is a -1, but I have 2 of them for the 1 calcium. Calcium is a 2 plus, but you should also know that because calcium is in group 2 of the periodic table, so it has to be a plus 2. Okay. So then the question is, what are we going to get? Let's look at the ions that are going to swap places. You're going to get your nickel 2. There's your 2 nitrates, your calcium, and your 2 chlorides. That is going to, let's see, so when they switch places, when the ions switch places, you're going to get nickel 2 chloride and calcium nitrate. So again, I need 2 of the nitrates to cancel out the plus 2 of the calcium. Okay, we go to our solubility rules. Nickel 2 chloride is soluble by rule 4. Calcium nitrate is soluble by rule 3. So we don't get a precipitation reaction. And here in a little bit, you're going to see that this is actually no reaction at all. But we can still write the chemical equation. And we're fortunate everything's actually balanced. So everything's soluble, so everything's going to be aqueous. So our formula equation, using that term very explicitly, nickel 2 nitrate calcium chloride. And then on the right side, we're going to get nickel 2 chloride. It's soluble, so it's aqueous. And calcium nitrate. It's soluble, so it's aqueous. And there's our balanced reaction equation. Again, you'll find out in a minutes that this actually means there's no reaction, and we'll see why. All right, so how do we describe reactions and solutions? So what we're going to start working with now are ionic equations. So again, this type of equation here is called your formula equation. You can take that and turn it into a total ionic equation and then a net ionic equation. The difference between the two is the net ionic equation shows the important part, the actual chemical reaction that's occurring because the spectator ions have been removed. And again, your spectator ions are ions that are not involved in the chemical reaction, and they're the ions that are the exact same on the left and the right of the arrow. So let's go back to one of our reactions. So our sodium chromate and our aluminum bromide. So we already did this one. So our formula equation, we remember, okay, so here's our precipitation reaction. That's our formula equation. Make sure I got all the numbers right. I think I do. Now, the next thing is the total ionic equation. And what we're going to do is take these compounds and we're going to break them up into their constituent ions. And you'll notice for the total ionic equation, we're not going to eliminate anything. Okay, so now pay attention. So see, we have 3 of the sodium chromates, but I have 2 sodiums in there. So 3 of those compounds at 2 sodiums apiece is going to give me 6 sodium ions. Then I'm going to have 3 chromate ions. I'm going to finish writing this out, but you get the point. See, 2 of the aluminum bromides at 3 bromides apiece. That's 6 bromide ions. Now the other side. So 6 sodiums. Bromides. Now what should I do here? Here's one of the keys to your ionic equations. You are only going to split apart aqueous compounds. If it's a solid, a liquid, or a gas, you're just going to leave it whole. And this is how we will end up at the net ionic equation, which shows you the important part or the actual chemical reaction that occurs. So this here is your total ionic equation. I split up everything I can. I brought down the solid aluminum chromate. And now we're ready to say, well, what are the spectator ions? Okay, so my spectator ions, you see I have 6 sodiums and 6 sodiums on the left and the right. I have 6 bromides and 6 bromides on the left and the right. Nothing else can cancel out. And so what I'm left with is my net ionic equation, which is everything that's not canceled out. Let's see. Okay, so that's going to be 2 aluminums plus 3 chromates is going to yield my solid aluminum chromate. This is my net ionic equation. And it's, again, the ionic equation after the spectator ions have been removed. And so now you see the actual chemically important part that occurred in this reaction. So let's look at, so we're going to go back to our other one, and we say, well, how do we know when there is no reaction? So, okay, so you remember our other reaction, everything was aqueous. So if I do I'll just start at the formula equation. Remember we had nickel 2 nitrate, calcium chloride, nickel 2 chloride, and calcium nitrate. Okay, now let's turn this into our total ionic equation. Okay, so we're going to have nickel 2 plus 2 nitrates plus calcium. Again, calcium is in column 2 of the periodic table, so you should know it's a +2. Plus 2 chlorides. Again, chloride is a -1 because it's in column 17. It's a halogen. Well, in its negative ion form, it's a halide. See, then on the right, again, you get nickel 2 plus 2 chlorides calcium, and then we're going to have to do nitrates. That's my total ionic equation. Now, if I go through, I can say, well, nickel 2 is the same to nitrates, calcium, and 2 chlorides. Everything cancels out. There is no net ionic equation. So this is no reaction. There could be other situations where there's no reaction. Let's say you try to mix a bunch of things together and nothing is soluble. They're not going to react, at least in solution. All righty. So let's do an exercise. What is the formula, equation, total ionic equation, and net ionic equation for this reaction here? So here you see we have potassium carbonate and magnesium iodide. Okay. Well, the first thing is to predict what the reaction is going to yield. So if I have my two potassiums, carbonate, you should know it's a 2 minus. It's one of your polyatomics. But if you don't, but each potassium is a +1 because it's in column 1 of the periodic table, group 1. And so if there's 2 of those to the 1 carbonate, carbonate has to be a -2. Now let's see. Magnesium is a group 2 element, so its ion is a +2. Iodine is a group 17 element, so its ion is a -1. And when those ions switch places, we are going to get potassium iodide and magnesium carbonate. Magnesium carbonate, again, is a 1-to-1 because the magnesium is a +2, carbonate's a -2. I only need one of each ion to neutralize. Potassium iodide, potassium is a +1, iodide is a -1. I only need one of each ion to neutralize. So I'm going to go to my solubility rules. Potassium iodide is soluble by rule 1. Magnesium carbonate, it's insoluble by rule 9. Okay, so now I can go ahead and put everything together, make sure I balance the equation, and write my formula equation. When you're doing your predictions, I'm not too worried about the phase on your ions. When you're doing your ionic equations, I am. So we're going to end up with, and on your assignment, you'll probably have more steps than this when you're balancing, but you may not. So if we have our potassium carbonate, that's aqueous, plus our magnesium iodide, that's aqueous. So then potassium iodide is going to be aqueous. And you see how on the left I have 2 potassiums and 2 iodides? That means when this compound is made, I'm going to have 2 potassium iodides. And it's aqueous, and there's only, on the left, there's only 1 carbonate, only 1 magnesium. So I only need 1 magnesium carbonate, but it is insoluble, so it's going to be a precipitate. Now, formula equation's done. Total ionic equation. Everything that's aqueous is going to split into its constituent ions. Anything that's not aqueous will not. So I'm going to have 2 potassiums. Carbonate. Magnesium ion. 2 iodides. On the right, I'm going to have two potassium ions, two iodide ions, and then my solid magnesium carbonate. And there's my total ionic equation. Now, for my net ionic equation, I need to get rid of spectator ions, which you'll notice is potassium. And the two iodides go. The net ionic equation is what's left. And so that's going to be magnesium ion, carbonate ion. It's going to yield the solid magnesium carbonate. Okay. Now, can we do stoichiometry using for these precipitation reactions? We've already done some stoichiometric calculations, and you're going to find that the rules are going to stay the same. It doesn't matter what kind of reaction it is. Your stoichiometry is still going to you're going to translate things to moles. You're going to do mole to mole comparisons, and you're going to solve your calculations by the same rules. So here it's like what volume of 0.1 molar sodium phosphate is required to precipitate all the lead ions from 150 milliliters of 0.25 molar. Let's see, what do we have there? Each nitrate is a -1. There's two of them, so it has to be lead 2 nitrate. Okay, so basically what it's saying is how much of the sodium phosphate will completely react with the lead 2 nitrate. Okay, so volume sodium phosphate, what we don't know. I'm just going to write down some things that can help me. And I want to make this list or I'll get points taken off my assignment. 150 milliliters is also 0.150 liters. My sodium phosphate is 0.1 molar. And my lead 2 nitrate point 0.350 molar. Okay, so I need to think about, all right, so let's do our sodium nitrate or sodium phosphate. Plus our lead 2 nitrate yields what? Well, the first question is, are our reactants even soluble? Okay, so this one is by rule 1. Let's see, and this one is also soluble by rule 3. Okay, so they're soluble, which means now I'm going to say, well, there's 3 sodiums plus a phosphate. Again, you should know phosphate is one of your polyatomic ions, but again, you say, well, there's 3 sodiums. Sodium is in group 1, column 1 of the periodic table, meaning it has to be a +1 when it becomes an ion. And if I have 3 of those +1s to the single phosphate, then phosphate has to be a -3. That's the only way they neutralize. Let's see, then I'm going to have my lead 2 and my 2 nitrates. And when these ions do their double replacement, I'm going to get sodium nitrate and then lead 2 phosphate. Okay, so again, lead has a +2, phosphate has a -3. So they have to meet at +6, -6. So I need 3 of the leads and 2 of the phosphates. Okay, and so then I'm going to say, well, what's the solubility on the right side? Sodium nitrate is soluble by rule 1. Lead 3 phosphate is insoluble by rule 10. So we have a precipitation reaction. Okay, so now I'm going to have sodium phosphate, lead 2 nitrate, then I'm going to have sodium nitrate, and lead 2 phosphate. So then you're going to go through your balancing process. And again, I want to see you working through this at least in some way, maybe not necessarily doing the list of numbers each time, but I want to see you working on your balancing. I don't want to see you just go from here to a balanced equation because, well, let's face it, you could AI that. I want to see your process. So when you once you get this balance, you're going to have 2 of your sodium phosphates. You're going to have 3 of your lead 2 nitrates. You're going to have 6 of your sodium nitrates. And you're going to have 1 of your lead 2 phosphates. And you need to get here because again, this is a stoichiometry calculation. You need these coefficients. And of course, that coefficient is a 1. You need those coefficients. Remember, those are your multimole ratios. Okay, so now we're able to say what volume of the sodium phosphate am I going to need to completely react the lead 2 nitrate? Okay, so remember I have 0.150 liters of my lead 2 nitro. And my lead nitrate is 0.250 molar, so that's moles per liter. And so of course, liter divides out. And then from my equation, you see I have 3 moles of the lead 2 nitrate to 2 moles of the sodium phosphate. So your moles of lead nitrate cancel out. I'm at mole. Now have a calculation that's in moles of sodium phosphate, but I want a volume of sodium phosphate. So now I have to divide by the, where'd that go? There we go. I have to divide by the molarity, the concentration of the sodium phosphate, which is 0.100 moles per liter of sodium phosphate. And so again, moles cancels out. I'm going to multiply this all up, multiply the top, divide by the bottom. And what I'm going to get is 0.250 liters sodium 3-phosphate. You can leave your answer like that, or you could change it to 250 milliliters of sodium phosphate. So you see, once you get your chemical equation figured out, the calculation is the same for a stoichiometric calculation. You're using your coefficients in your equation to figure out how much of one compound you need in reference to another compound. All right, so we'll continue on with chapter 4 tomorrow. We may finish the chapter. I'll have to see, but we will definitely continue on. All right, talk to you later.